Hello, welcome back to Aerospace and Mechanical Engineering Lab 2. Today we're going to talk about plate buckling and the DIC test. Okay. So the objective of these labs are to study the buckling of planes and strain field measurements, to understand the difference between the point measurements of a strain and the field measurements of a strain, and we also want the students to learn how to use a DIC device. DIC stands for Digital Image Correlation, to make field measurements, and we want the students to learn how to use or how to perform any strain field analysis. In your lab reports, you don't have to do any calculations, but the idea is for you to calibrate the DIC system using the provided instructions to create an appropriate sample for testing and to produce the strain field showing the plate buckling, and eventually to summarize all of this in your lab report and discuss how you think we should measure the critical load of buckling for a plate. We already know how to do this for a beam, for a column, for an Euler column, but we don't really know how to do this for a plate. And I only want to see a discussion. Essentially, I want you to look it up online, read a couple of, or maybe one journal or one small part of a book and summarize it. This is not, I don't really ask you to do anything comprehensive here. So there is no calculations. It's just doing the test, summarizing the test, and a discussion about how to calculate the critical buckling load for a plate. Okay, so plate buckling is an important part of industry. We have to be mindful of plate buckling in whatever we design. You can see examples of plate buckling in two different structures. These are skins of an this is a skin of an aircraft essentially, and this is again the skin or a stiffness of a different aircraft. As you can see, because of the plate buckling, we can observe some debonding between the stiffener and the skin, which is not desired, of course. Okay, so how can the plate buckling happen? We can have a uniaxial compression, which essentially means that you apply compressive loads to two sides or one side of any plate, and it will cause deformation like this, right? We can have different modes of buckling for this scenario as well. And we can have different modes of buckling for all scenarios, which means that based on your load, the deformation shape is going to change. Shear applied to an example of a stiffener, as you can see, it looks like an I-beam, can cause a plate buckling in this direction. You can see the deflection intensity here. So the buckling direction changes when you apply shear, but the buckling happens nonetheless. Okay, we can have plate buckling on cylindrical shapes and spherical shapes by applying a compressive load or a shear load, and the idea is analyzing all of these analytically is basically impossible. You give it a very good value understanding. We have a couple of empirical equations, but we don't really have a real deterministic model to measure the buckling load for plates or spheres or cylinders. Again, other examples of where plate buckling becomes important, how to actually prevent it. We have different types of methods that are going to help us prevent or strengthen our design to have higher buckling loads, like vertical stiffeners, flange holes, ISO grids, and sun wave designs. But what makes the plate buckling difficult? The initial imperfections that we need to include in any analytical model. Curve geometry always makes any analytical modeling analysis impossible, basically. And also, whenever you are moving from a one-dimensional or two-dimensional rod or column to a three-dimensional space, understanding the supports that are necessary for your analytical analysis is going to be difficult. On inelastic behavior of material, local inelastic behavior can actually make all of this analysis difficult for us. Okay, so what are the solutions? The solution is to do a lot of tests, thousands of tests, and develop an empirical method or use numerical methods. We are going to talk about the first one today, essentially doing the field measurements of any plate, and we will discuss the numerical methods later on in lab 8. Okay, so what is the method we want to use? We want to use digital image correlation, or for short we call it DIC. DIC is a computer-based process to obtain a two-dimensional or a three-dimensional full field surface information. The key term here is a full field surface information. So we don't really have a point measurement anymore, like a strain gauge. Strain gauge gives us the strain at a specific point, but this is not a point measurement. This gives us a field measurement, and that's what makes the DIC a very powerful tool in our analysis arsenal. Essentially, what happens is you have to create a pattern, a speckle pattern on your sample, and track the movement of the dots on this speckle pattern. And we're going to see all of these later on. It essentially this method takes advantage of the fact that the stress is going to change the thickness and the optical properties of the speckle pattern, the intensity essentially that your cameras can read. We're gonna see a lot of all of those later on. But let's talk about the point measurement a little bit. Point-wise measurements, we can use strain gauges as we have seen before to relate the changes in resistance during the elongation to the elongation and a strain itself through a correction factor. Okay, so this is a very robust method. This is a very useful method. This is a very useful sensor strain gauge that we can use to measure the strain. But the problem with it is it only gives us a strain at a specific point, which is again helpful in a lot of cases, but for a plate buckling analysis, for example, not that helpful. We need to have a bigger understanding of the deflection that is happening throughout our field. Okay. And so if you want to use a strain gauge to do field measurements, you have to install a lot of strain gauges. Like we have installed 1, 2, 3, 7 strain gauges on this specific sample. But for these 7 strain gauges, we still have the problem of not seeing the strain at the locations where the strain gauge is not installed. So what happens is we install a lot of strain gauges and then we interpolate the data to find the field of a strain. But this way, we are going to not see a lot of deformation and deflection information. Right? For example, if you apply compressive load here, you might see a buckling happening at this specific location, but these 2 strain gauges are not going to see that buckling here. And if you perform an interpolation between these 2 strain values, you are not going to see the correct information for the buckling that happens here. Okay. So to overcome this problem, to fix this problem, a couple of engineers in our department actually tried to develop this method or try to perfect this method. And again, this happened in our department. This is one of the points of pride for our department, that the digital image correlation was developed here, was made available. There is a company in Colombia that works closely with us. It's called Correlated Solutions, and they are making devices that are sold everywhere to companies, to universities, to help them do field measurements. But how does it work? It's essentially very simple. You have a camera installed in front of a sorry, you have a camera that is installed in front of a sample, and you take a lot of pictures of the sample while of this specimen while you apply a load to it, and then these pictures are going to be processed by a computer that is going to change the movements of the speckle patterns as you apply the load. So this means that we have to make sure that our specimen, our sample, is ready for the analysis. How can we make it ready? By creating a speckle pattern. What is a speckle pattern? Essentially just a white background with dots on it. We can have a large speckle pattern like this, or we can have a very fine or moderate speckle pattern like the picture on the left. And these are used for different types of analysis. We are going to focus on just a moderate speckle pattern in this lab. The idea is, again, you are going to take a picture of this specific instant in time where you apply a specific load, and then you are going to change the load. This point, for example, is going to move here, and you are going to track the movement. This movement tracking that is done for all of these speckles is going to help us calculate the strain. Okay, let's move on to this slide. Essentially, again, we choose a point and then we track the movement at different times as you apply the load or change the load. Okay, one of the problems we face with in this type of analysis is the fact that there may be deformation in your initial pixels, and we have to deal with that. And these deformations are actually going to give us the field measurements that we want. So these are useful that we can capture this. Well, the idea is you have to create a subset in your element and do the measurements in your subset. So this is done by the computer. The fix is done by the computer. You don't really need to worry about the background information about this. But essentially, the computer uses this sum of square differences functions for all of the points in your sample. All of the points of interest, all of the field of the interest, right? And it's going to give you a pattern like this, which the red, it's a heat map. The red is going to give you the highest amount of strain, and the blue and the darker zones are going to give you the lowest amount of strain. This is what we want to get out of it eventually. Again, think of an example of this. We have a very image that is divided to it is a 9 by 9 pixel image. We have 81 pixels in the sample. Some of this is colored black and some of this is colored white. As you apply the load, the black part is going to move, as you can see, like this. And this movement, the changes in intensity in each pixel, is going to give us, like, for example, look at this specific pixel. The intensity of it is 0 the beginning. When you apply the load, the intensity becomes 100. Based on these changes in intensity that we record using the cameras, we can calculate the strain of the material. The device looks like this. You have a sample and you have two cameras pointing at it. You create pictures. As you can see, this is as a crack is propagating in our sample, and this gives us how much deformation you're going to see as this crack propagates. Another example of strain field measurements. As you can see, it gives us the information about all of the field, not just one part of it. And the device we're going to use looks like this. This is the DIC education device. They have two lenses installed and a light source to make sure your sample has enough illumination, has enough light on it, so you can take appropriate pictures. We don't really need to use the two cameras. The two cameras are used for three-dimensional analysis. Our analysis here is a two-dimensional analysis, so just one of the cameras is going to be enough for our analysis. The first thing you want to do is to do calibration. So essentially just take a picture of a calibrating sample to tell the software so the software understand how to measure the amount of change you have in your system. And then you will be given a plate that is already the pattern on it is already there. You don't really need to do anything about it. Just apply load to it and you calculate the strain. Please make sure to watch the video for the lab. Again, there are no calculations for this lab. We just want you to understand how to calibrate a software and how to make strain field measurements. Have a good rest of your day, and please let me know if you have any questions.